Welcome back to the deep dive, where we take concepts that, define modern IT infrastructure, these systems that are just running quietly beneath the surface, and we explore them. We get into enough technical detail that you can walk away feeling, well, truly informed, ready for that next technical meeting or even a certification exam. Today, we are tackling what I think is the great white whale of data management. We're talking about data protection,
hmm
and specifically the single greatest challenge in protecting mission-critical data, especially in like a high-transaction enterprise environment. And that challenge, it sounds simple. How do you get a perfect copy of data when applications like SQL Server or Exchange are actively writing to it,
Constantly changes.
constantly changing it, and keeping the files locked 24/7? I mean, if you try to take just a simple file copy during all that activity, the backup you get isn't just corrupted, it's a useless mix of old and new data blocks.
It's garbage.
Yeah, it's like trying to photograph a moving car with a really long exposure. The final images, it's always going to be inconsistent and blurry. So, our mission today is focused exclusively on the technical blueprint. We're using Module 2, Lesson 9 from our source material to unlock the mechanics of the Microsoft Volume Shadow Copy Service, or VSS. This framework isn't just some utility, it is, and I'm quoting our sources here, mission control for snapshots.
That's a great way to put it.
So we're going to do a deep dive into the specific components, the intricate, coordinated dance VSS performs to make sure your backups aren't just copies, but are fully consistent, usable, and maybe most critically restartable images of your running applications.
And this framework absolutely deserves this level of scrutiny. VSS is really the unsung hero of application availability. And it's important to stress this isn't some optional feature. It is the foundational infrastructure for all modern Windows data protection. We're talking going back 2 decades.
Yes, decades, wow.
Yeah. If you're running anything from Windows XP and Server 2003 all the way up to the current server releases, and you need a hot backup of applications like Active Directory, SharePoint, or the database layers underneath, VSS is the only sanctioned reliable interface. Understanding its components, the requester, the writer, or the provider is, well, it's paramount to diagnosing why your backup jobs succeed or, let's be honest, more often why they fail.
Okay, let's unpack this. And I think we have to start our conversation in the past. We need to look at our first segment. The chaos, the technical pain points, VSS was specifically engineered to eliminate. So before VSS, the life of a sysadmin trying to, maintain data integrity was often defined by anxiety. The core issue, like you said, was that simple inability to guarantee consistency during a copy. But let's zoom in on what that inconsistency actually looked like at the file level.
Right, so when we talk about application consistency, what we're really talking about is making sure that all the related parts of an application, so the main database files, config files, and crucially the transaction logs, are all captured at the exact same moment in time.
A single moment.
A single moment. Before VSS, if a backup started, it might take minutes, maybe even hours to complete. And all that time, the application is still running. It's still committing transactions. So a single database transaction might involve, say, writing to the log file first and then updating 2 separate database data files.
Okay.
Now, if your backup job copied the log file, but only one of those 2 data files was updated before the backup program moved on, the resulting backup set now contains mismatched data. That backup is inconsistent, it's unrecoverable, it's simply junk.
And if those files were open exclusively by the application, which they usually are, the problem's even worse.
Oh, indeed. If the files were open with an exclusive lock, and that's standard practice for critical database files, backup programs often have to just skip them entirely, which leaves these huge holes in your recovery plan. But even trying to avoid the skip just introduced this risk of data corruption.
Yeah.
It often meant the sysadmin had to choose between 2 really bad options.
The first bad option being, relying on application-level consistency checks after you restore, which often failed.
Right.
And the second, and I think arguably the more painful option, was what you could call the nuclear option for getting integrity.
The necessity of service interruption.
Yeah.
To genuinely guarantee a clean, consistent backup that reflected a static state, the traditional approach required either suspending the application or, more often, just terminating all the running programs associated with the data you're backing up.
So you had to literally stop the database.
You had to halt the database, wait for all the transactions to flush out of memory, and only then could you perform the copy. For any environment aiming for high availability, which is, let's face it, every modern enterprise forcing service downtime, even for an hour in the middle of the night, became a completely unacceptable operational requirement. VSS had to solve this 247 availability challenge first and foremost.
So, okay, we've got inconsistency, file locks, and the requirement for downtime. But the complexity was just, it was magnified by the fragmented hardware landscape, wasn't it? Let's talk about that vendor fragmentation and the technical nightmare it created.
Well, before VSS gave everyone a unified API, the storage vendors that supported volume capture, which is just the fundamental act of taking a storage snapshot, they each provided their own proprietary drivers and mechanisms.
So everyone had their own way of doing it.
Everyone had their own way. This meant backup software developers had to write and then maintain this incredibly complex code just to talk to dozens of different drivers for different storage arrays, different RAID controllers, different HPAs. It was a mess.
Which meant, I'm guessing, no central coordination was possible if you had, say, storage from different vendors.
Oh, exactly. I mean, imagine a single server connected to 3 different storage systems from 3 different vendors. To create a cohesive, consistent backup across the entire application stack, all 3 of those vendors' capture mechanisms needed to freeze the data at the precise same millisecond.
And without VSS.
Without VSS, there was no central mechanism to coordinate that data freeze across different hardware. And even if you could somehow technically coordinate the volume freeze, many of these proprietary systems, they just couldn't communicate with the running applications to make sure data was flushed from the host memory onto the physical disk before the snapshot pointers were created.
And that brings us right back to the integrity-destroying issue known as torn writes. Let's spend a moment defining this clearly for everyone listening, because it's really the ultimate failure that VSS prevents.
A torn write is a very specific form of data corruption. So imagine a database system trying to write a new data block. Let's say it's 8 kilobytes to the disk. The application tells the operating system, perform the write. The OS might start the process, but before the entire block is physically committed to the platter or to the flash memory, an interruption happens.
Like a power failure
Or, in this pre-VSS world, an uncoordinated volume snapshot. So the snapshot captures the disk state mid-write, freezing a half-updated data block. This leaves the file structure corrupted, or torn, because the backup now reflects an incomplete transaction.
So VSS was designed to fix this. It forces the application, the writer, to flush its caches and stop I/O the freeze before the capture mechanism the provider locks the pointers.
Exactly. It provides a single, unified communication structure to get rid of all the guesswork and the proprietary driver chaos.
That structural unity uniting the application state, the OS file system, and the hardware snapshot mechanism, that's really the core promise that VSS delivers. It shifts the burden of coordination from the backup vendor and the sysadmin to the centralized Windows OS framework. And this brings us right into segment 2, understanding the components required for this delicate coordinated effort.
So to achieve this coordinated zero downland consistency, VSS relies on what's called a tripartite architecture. You can think of it as a highly specialized engineering team.
Okay, a team. I like that analogy.
Yeah, so you've got the requester, who is the project manager, you've got the writer, who is the application specialist, and then you have the provider, who is kind of the field technician responsible for the physical task. And all 3, they have to execute their roles perfectly.
Let's start with the project manager, the requester. This is probably the component our listeners are most familiar with, since it's built into their backup software.
That's right. The requester is any application that uses the VSS API to manage shadow copies. So typically, yeah, it's a third-party backup application, think Veeam, or Windows' own data protection manager, DPM. Its role starts with the initiation. It accepts your request to make a copy, but its responsibilities are actually far-reaching. The requester doesn't just ask for the snapshot. It orchestrates the entire process, including the data transfer that happens after.
What are its specific long-term responsibilities then, beyond just kicking it off?
They fall into 2 really critical categories: lifecycle management and metadata retention. So the requester manages the cataloging and the archival of the shadow copies. It decides where the backup data goes and how long the shadow copy itself should stick around on the system. And crucially, the requester maintains the state information about the whole operation in a document called the Backup Components Document, or BCD.
Okay, let's delve into the BCD for a moment, because this is where the deep dive detail really becomes necessary. Why is the requester retaining this detailed state information, and what specific technical details are in that BCD?
Well, the BCD is essential because recovery is often way more complicated than just copying files back. The BCD is the requester's blueprint for restoration. It details exactly which components were successfully included in the backup. For example, if you backed up a complex system like Exchange, The BCD would list the specific storage groups, the mailboxes, the transaction log paths, and the state of the system at the moment of capture.
So it's the recipe for putting it all back together correctly.
It's the full recipe. This metadata allows for really granular recovery later on. If you need to perform a full bare metal recovery, a BMR, the BCD ensures the requester knows the precise location and configuration of all the system state components. Without the BCD, the backup files themselves are just data. With the BCD, they become an intelligently structured application image.
So the requester defines the scope of the mission and records its success. But for that mission to even be valid, it needs the writer, the application specialist, to prepare the data.
Precisely. The writer is what elevates VSS beyond just simple volume management. A writer is an application-specific service component. So if you have SQL Server running, its writer is active. If you shut SQL down, the SQL writer just disappears from the VSS ecosystem. This component is written by the application vendor, so Microsoft for their own applications, or third parties for theirs, to communicate intimately with the VSS framework.
And if an application isn't VSS aware, if it doesn't have a writer...
Good question. If it doesn't have a specific writer, VSS falls back on the generic system writer. This provides basic file system consistency, but you don't get those application-level guarantees.
Okay, so let's focus on the writer's key functions, particularly in achieving that critical consistent state we talked about.
The writer performs 3 essential tasks. First is discoverability. The requester needs to know what files even belong to the application. So the writer exposes all the required data stores, the paths to the data files, the registry keys, the logs, and it communicates the specific requirements needed for a successful backup and, later, a restore.
And second is that critical phase we mentioned earlier, data consistency. How does the writer actually achieve this complex, multi-step consistency flush?
The writer ensures the data on the disk is transactionally consistent before the freeze ever happens. It executes a series of internal cleanup tasks, and these are often unique to the application. For database, for example, it completes any open, pending transactions. It rolls the transaction logs, ensuring all committed data that was in memory has been written down. It flushes the application's internal caches.
So it's a full data housekeeping routine.
It is. This guarantees that when the snapshot is taken, the application can legitimately say, all my data is safely on disk and I am at a known restartable state. This synchronized flush is the antidote to those torn writes and ensures the consistency level is high enough for immediate application recovery.
And finally, the writer is the key participant in the actual synchronization event, the freeze and thaw.
Yes. The writer doesn't just prepare the data, it communicates how that data should be restored using something called the writer metadata document. This is an XML file, often quite extensive, that describes every file, every volume, and the application's required restoration procedure.
So it's another blueprint, but this one is from the application's point of view.
Exactly. Once this document is delivered to the requester, the writer enters a listening state. VSS then signals the writers to perform the freeze, which is the act of quiescing or pausing I/O write requests. The writer temporarily halts all incoming writes to the volumes it manages. Moments later, after the snapshot is taken, VSS signals the thaw and the writer resumes normal operation. This coordinated freeze-thaw dance ensures the minimal possible impact on the running application.
So we have the requester defining the mission, the writer prepping the application. Now for the field technician, the provider, the component that physically executes the volume capture.
The provider is the mechanism responsible for creating and maintaining the shadow copy. It operates at a lower level than the application, interacting directly with the file system filter drivers. It receives the metadata describing the scope of the volumes to be captured, and then uses an I/O interceptor to manage writes to the source volume and track any changes.
Let's distinguish clearly between the two major types of providers, because this has massive performance implications for anyone using this.
It really does. First, you have the software provider. This is the default sister component that comes with Windows. It operates above the OS file system, and it uses host CPU and memory resources to intercept I/O requests and manage the change tracking. It's flexible, it supports any local NTFS disk, but it puts the resource burden squarely on the production server.
And the alternative?
The alternative is the hardware provider. This is a proprietary driver supplied by a storage vendor, your HBA, your RAID controller, your external array. And the critical difference here is that the creation of the shadow copy, the I/O interception, and block tracking is offloaded entirely to the storage array itself.
So it's not using the server CPU at all?
Or at least not consuming any significant host CPU resources. This is absolutely essential for high-throughput environments, and it enables true off-host or serverless backup operations. So the choice of provider really determines whether your snapshot creation is a background task handled by dedicated storage hardware or a competing CPU task on your production server.
Understanding the requester, writer, and provider, the boss, the specialist, and the copy machine is absolutely the key to understanding VSS. So now let's dive into that copy machine's internal workings in segment 3. How does it capture a massive volume almost instantly without actually moving all the data? The genius of VSS, and the provider specifically, really lies in its mechanism for efficiency. We've established that a snapshot doesn't immediately copy all the data because that would be prohibitively slow. Instead, VSS uses the copy-on-write principle, or CalW. This is a pointer-based replication mechanism that provides an instantaneous, consistent view of the volume.
And that concept of instantaneous capture is so crucial. When the requester asks for this snapshot, the provider doesn't kick off a huge data transfer. It immediately establishes a new logical construct, the virtual volume. This is essentially just disk space that's been allocated for the save location.
So it's just empty space at first?
Initially, yeah, this virtual volume is empty, yet the snapshot is immediately accessible to the backup application.
Okay, so if the snapshot volume is empty, how does copy-on-write make sure that the historical data, the blocks that existed at the point in time of the freeze, are preserved if the source volume starts getting new writes?
This is where that I/O interception driver, which sits at a specific layer in the OS stack, comes into play. It monitors all write requests that are destined for the original source volume. Let's walk through the technical specifics of what happens when the application tries to change data after the snapshot has been successfully created. First, the application sends a request to write a new data block, let's call it block A, to the source volume. Second, the provider's I/O interceptor immediately catches this request before it gets to the physical disk. Third, the interceptor checks its map. It identifies the current content of block A on the source volume.
Okay, so it knows what's there right now.
Exactly. Fourth, and this is the copy-on-write step, before the new write is allowed to proceed, the provider makes a copy of the original content of block A and moves it to that allocated space in the virtual volume, the save location. And fifth, only after the original block is safely preserved in the save location, the interceptor allows the new write, the change, to proceed to the source volume.
So the source volume always has the most current data, while that save location only contains the blocks that have changed since the snapshot. It's preserving the historical view. It's this dynamic, ongoing process of saving the before image whenever a write happens.
Exactly. The virtual volume doesn't contain a full copy, just the differences, the deltas, that are necessary to reconstruct that original point-in-time view. And this is incredibly efficient. Now, let's look at the read side. How does the backup application use this CalW structure?
Right, because when the backup app starts reading the snapshot, it's reading a volume that doesn't physically exist as a full copy.
Correct. When the requester reads, say, data block X from the shadow copy, the provider consults its map. If data block X on the source volume has not been modified since the freeze moment, the provider just directs the read request directly to the source volume.
It reads from the live volume.
It reads from the live volume. But if data block X was modified, meaning its original content was copied to the save location, the provider redirects the read request to the virtual volume, and it retrieves the historical point-in-time version of that block.
That is the crucial insight that I think often surprises people. The backup is often reading most of its data directly from the active source volume, especially if the change rate is low. It only consults those delta blocks when a change has actually occurred. And this explains why the creation time is near instantaneous and the read operations are only slightly slower than reading the source itself.
And this mechanism, it imposes specific technical requirements. VSS has to operate at a level that can reliably manage these interceptions, which is why it is strictly limited to NTFS volumes. The underlying structure and metadata management of NTFS allow for this high degree of I/O control. Older file systems like FAT or FAT32, they just don't have the necessary robustness or capabilities to support the CalW driver.
Let's talk about the practical configuration implications for this virtual volume, the save location. Especially for admins who are setting up backups on large systems, the sizing matters hugely, doesn't it?
It really does. By default, Windows sets the virtual volume to 10% of the size of the source volume, with a 300 megabyte minimum. But in high transaction environments, 10% might be completely insufficient, especially if you plan to keep multiple shadow copies, or if the change rate, the churn on the source volume is very high. You do have the flexibility to configure the volume size to be essentially unlimited.
And the physical placement of that save location, that dedicated space, does that affect performance, I'm thinking I/O contention.
Absolutely. The default location is the same partition as the source volume.
Yeah.
So, for example, if you're backing up the C drive, the virtual volume for the save sets is also on C. If C is also the location of your highly active database, every single write transaction is now triggering two I/O operations, the write to the destination and the copy on write operation that saves the original block.
And they're competing for the same disk resources.
They are competing for resources on the same physical disk. So for high-performance systems like domain controllers or database servers, moving the virtual volume to a separate physical partition or a separate storage spindle minimizes this I/O contention. It offers a significant performance improvement during that copy-on-write stage. It's a key optimization strategy.
So we've identified the components and the underlying CowW mechanics. Now let's tie it all together in segment 4, mapping the high-stakes, step-by-step choreography that defines the VSS backup workflow.
The VSS workflow is really the culmination of the coordination between these three components. It's a 5-step process where timing is everything, ensuring that application consistency at the precise moment the copy is locked in.
Starting with step 1. The user clicks Run Backup, and the requester springs into action.
Step 1. Initiation. Yeah. Right. The requester, so your backup application, makes the critical VSS API call, formally asking the VSS service to create a shadow copy of the specified volumes and components. This request includes the requester's specific needs, like whether it needs a full backup, a copy backup, or a differential copy. VSS logs this request and begins the orchestration. And this logging is crucial for auditing and troubleshooting later, because VSS is highly verbose in its event logs.
Step 2 is where we see the most complex synchronization happen. We're moving from requester to writer and prepping the data for that moment of truth.
Step 2. Preparation and freeze. The VSS service notifies all the relevant application-specific writers. Each writer then begins its preparation sequence, executing its internal tasks, completing transactions, flushing caches, rolling logs. The writers then exchange metadata, submitting their finalized writer metadata documents, those XML blueprints, back to the VSS service and the requester. This confirms they're ready.
Okay, so everyone's ready.
Everyone is ready. VSS then issues the critical Prepare for Snapshot API call and immediately directs the writer to execute the freeze operation, temporarily halting I/O write requests. And crucially, the VSS service itself then flushes the file system buffer and freezes the file system metadata.
That sequence of events, writer preparation, writer freeze, system freeze, that's the point of no return. What's the technical marker of consistency here?
The crucial takeaway is that the instant the write I/O is frozen, that marks the confirmed consistent point in time, or PIT. The system guarantees that all data pertaining to the application is on the disk, it's synchronized, and no new writes are permitted until the snapshot process completes. The goal is to minimize the duration of this I/O freeze, ideally keeping it under 5 seconds, sometimes even a fraction of a second. That's why the pre-preparation by the writer is so important.
And once that consistency is locked down, we move instantly to step 3, snapshot creation. The provider is now officially activated.
Step 3. Snapshot creation. VSS notifies the designated provider software or hardware to create the shadow copy. The provider isn't moving data, remember, it's executing the CowW mechanism. So it rapidly creates the internal volume mapping and allocates the space for the virtual volume. The provider then returns its own metadata, confirming the location and the identifier of the newly created shadow copy volume. This mapping is also based on an XML definition, effectively locking in the pointers to the current state of the source data.
And this phase has to be executed really rapidly to keep that system freeze as short as possible.
Precisely. The speed of the provider, particularly if it's a hardware-accelerated one, is paramount here. The moment the pointers are locked and the mapping is created, the system has to immediately proceed to step 4 to minimize the application impact.
Which is the immediate restoration of service.
Step 4. Thaw and resume. As soon as the provider confirms the snapshot mapping is successful, VSS sends the thaw instruction to the writers and unfreezes the file system. The production server immediately resumes normal write activity, having experienced only a brief quiesced state. Concurrently, VSS transmits the location and handle of the new shadow copy volume back to the requester, completing the internal VSS cycle. The production application is back online, and the consistent snapshot is now ready to be used.
And finally, step 5, the actual work of moving the data can begin.
Step 5. Backup execution. The requester now has the location of the shadow copy volume. It treats this snapshot as the source data and begins the backup process. And because the requester is working against a fixed, consistent copy, It encounters no file locks, no data inconsistency, no in-use files. The files are just static and readable. This step can take hours, but it doesn't affect the production server's consistency at all because the work is being done against a frozen shadow copy.
And this is where that concept of off-host backup becomes really tangible. If that consistent snapshot can be mounted to a proxy backup server, the production server is entirely free from the burden of data movement.
That is the ultimate architectural payoff. That proxy client can do all the heavy lifting, the data transfer across the network, compression, deduplication away from the production machine. This dramatically reduces the I/O and CPU overhead on the primary application server, which enables high-frequency, non-disruptive backup schedules. The snapshot can be kept for quick local restores or used purely as the source for the transfer to secondary long-term storage.
That structured five-step dance is the core mechanism allowing critical file systems, domain controllers, and databases to achieve perfect consistency while maintaining that 24/7 availability. Now that we've fully mapped the blueprint, let's explore some of the real-world implications and consequences of VSS configuration, starting again with that choice between software and hardware providers.
The provider choice isn't just about vendor preference. It's a big performance and resilience decision. The native Windows software provider is the baseline. It's driver-based, it's reliable, and it uses host resources. What this means is that under a heavy transactional load, the CPU cycles needed to intercept every single I/O operation and manage that copy on write cache. They hit the production server directly. For small environments or low-turn systems, this is probably fine.
But for high transaction volumes, the hardware provider is almost mandatory, isn't it?
Oh, absolutely. The hardware provider shifts the responsibility of I/O interception and cache management to dedicated hardware, the storage array controller. The host just communicates to the array, hey, take a snapshot, and the array executes the task instantly using its own resources. The host CPU load is vastly reduced, minimizing the performance impact. Furthermore, many hardware providers can offer functionality beyond VSS, like instant volume cloning or remote replication, integrating the snapshot into a much broader disaster recovery strategy. For any enterprise environment that's prioritizing RPO and low impact, investing in hardware providers is a necessity.
You mentioned that VSS can maintain multiple versions of files. Let's delve into that retention capability. How is that 64 version limit managed, and what happens when the allocated save space runs out?
The retention management is surprisingly simple, but it's crucial. VSS supports tracking up to 64 unique versions of the same file across multiple shadow copies, as long as the virtual volume, the CAUTOB cache, has enough space. And Windows automatically manages this retention using a FIFO principle, first in, first out, specifically focusing on space allocation.
So it's all about the available space.
All about space. If the allocated disk space for the virtual volume starts to become insufficient because the source volume has undergone extensive changes, Windows prioritizes the creation of the new snapshot. It will automatically and silently delete the oldest shadow copies to free up space in the save location. This prevents the virtual volume from consuming all available disk space, which is a safety mechanism designed to protect the integrity of the production server. But, administrators have to monitor the utilization because relying solely on this automatic mechanism might mean losing recovery points faster than you anticipated if the underlying volume change rate is higher than you expected.
And circling back to the problem VSS solved, the inability to back up active and open files, VSS handles this inherently. But how does the backup application perceive those locked files now?
The backup application doesn't interact with the locked production files at all. It interacts with the shadow copy volume. And since the shadow copy is a static read-only representation of the volume at the PIT, every single file, including those that were locked for writing by the application, appears as a completely accessible static file.
Yeah.
This ensures comprehensive protection. Without VSS, any traditional file-level backup trying to access a locked database file would just fail with an access denied error. With VSS, that same file is copied seamlessly from the snapshot.
Let's end by reiterating VSS's profound importance for these complex multi-component applications like Exchange or SQL Server. Why does VSS guarantee a redo consistent snapshot, a state that traditional file snapshots just can't achieve?
Consistency comes down to the synchronization that's achieved in step 2 of the workflow. For hot backups of complex applications, VSS doesn't just promise that files are closed. It guarantees transactional integrity. Because that application-specific writer executes its pre-snapshot routine completing open transactions and writing all necessary transaction logs to disk, the resulting snapshot is at a state of being crash-consistent and redo-consistent.
Okay, so what does that mean in a practical restore scenario?
It means if you were to restore a VSS-captured snapshot of a database, that database would be capable of immediately starting up and performing its own internal recovery checks. It wouldn't find any incomplete data blocks or torn writes because the writer guaranteed all that data was flushed to disk before the freeze. The database knows exactly where its recovery point is because the data and logs are perfectly synchronized. This is just theoretical. It eliminates the uncertainty and the recovery failure potential that's inherent in uncoordinated snapshots.
This has been an extensive deep dive into the architecture and the workflow of the Volume Shadow Copy service. We've mapped the blueprint, detailing how the requester, the application's writer, and the provider collaborate through that copy-on-write mechanism to deliver perfectly consistent, non-disruptive, point-in-time copies of active data. This framework is truly the technical foundation for modern business continuity.
We have established that VSS eliminates the physical necessity of downtime for a consistent backup. But this elegant solution introduces a new set of strategic challenges for you, the professional, to consider as you design your recovery strategy. Remember, VSS snapshots, regardless of whether they're using the software or the hardware provider, are fundamentally pointer-based replicas residing in a cache on your underlying storage system. The data blocks are still stored on the same physical disks as your primary source volume.
Okay, that's a critical point.
It is. This means that the consistent recoverable image, the snapshot, is inherently dependent on the health of the original storage array and the source volume itself. If you experience a catastrophic hardware failure, a complete disk array failure, or a physical loss of the volume, the snapshot cache is lost along with the production data, so you lose everything. You lose everything. Therefore, the strategic question shifts. If VSS allows you to create these instant, consistent recovery points, and you rely solely on those fast snapshots for operational recovery, how will you break the physical dependency link? The reliance on the primary volume introduces a single point of failure that the initial desire for a backup was trying to eliminate in the first place. How do you plan to extract that VSS consistent data to separate immutable media to ensure absolute resilience against physical catastrophe? That extraction step is the true measure of your overall disaster recovery posture.